The terms that I'm going to go through today for VT reentrant sites are a exit site. So let's imagine we have a VT circuit here. So we have some depolarization rotating around an island of scar, and then that enters what's called an entrance site. So this is an entrance site because it's where depolarization enters this scar tissue, and then it travels in a constrained diastolic isthmus. So this is called a diastolic isthmus. Isthmus just basically means like corridor. And so there's this corridor of surviving but probably very diseased myocytes between these islands of scar. So you get some slow conduction there. And then depolarization exits the scar, and that's called the exit site. And then outside the scar region is called the outer loop, because this outer loop is not really constrained by scar tissue. And you also have these regions called adjacent bystanders, and these adjacent bystanders are regions that are within the scar and I guess electrically adjacent to diastolic isthmus, but don't actually participate as part of the VT circuit. So the ones in brackets here don't participate as part of the VT circuit, and the ones that are not in brackets do participate as part of the VT circuit. So depolarization or VT reentry circuits utilize kind of the exit site, an entrance site, a diastolic isthmus, and usually an outer loop. Sometimes there's something called like an inner loop as well, and that's where you have like another scar here. So let's say there's another island of scar, or whatever that barrier is, for physical barrier for conduction, and then instead of being called the outer loop, this would be called the inner loop, because it's also constrained by scar tissue, so it might be called the inner loop in that circumstances. But I don't really want to make the distinction between inner loops and outer loops for the purpose of this video, because it doesn't have as much of an impact on VT diastolic isthmuses that for today's purpose at least. So what is the exit site? So depolarization travels around the outer loop, it enters the scar, it goes through the diastolic corridor, and it exits the constrained scar, and we call that the exit site. And that's where the re-entry arrhythmia of VT exits the constrained scar through the diastolic isthmus, and then it exits the exit site, where I guess that you could say that's where the complex scar, where VT is, it kind of meets the rest of the myocardium. And depolarization exits this kind of diastolic corridor and starts to depolarize the rest of the ventricle now. So the rest of the ventricle starts to depolarize around from this location. So when you're localizing VT, scar-related VT, using the ECG, and you're saying, oh, this is a scar-related VT coming from the anterior basal portion, what you're saying is you're actually localizing the exit site of that VT, because the exit site is what dictates VT QRS morphology, because the ventricles are both depolarized from the exit site. And so this means that your QRS morphology is dictated by where your exit site is. So QRS onset usually occurs after the exit site. So here, not enough voltage is being generated to cause deviation from the isoelectric line, right, in this kind of region here. And then once depolarization exits the exit site, it can now start depolarizing a lot of myocardium, and now you get your QRS onset, right? Now there can be multiple exit sites. However, there usually is an exit site that is the dominant exit site, because there's a shorter conduction pathway, and we're going to go through that in the next slide, what exactly I mean by that. So let's reimagine our scar here. So I've opened up another exit site here. So the only difference between this scar and on the previous slide is I've opened up another exit site here as well as here. So now you can kind of imagine that VT rotates around this way, because this is a much shorter kind of rotation than this, right? It's shorter. So this would now be the dominant kind of VT morphology, right? So this will be the dominant VT reentrant circuit, I beg your pardon. So this is where the reentrant circuit now is. This is what we call the active circuit in blue, and in green, and this should also be green here, so I'm going to draw that in green. In green is the passive circuit, right? Because you can ablate everything in green is kind of as much as you want, and you're not going to terminate VT. Or maybe if you ablate here, you'll terminate VT. But really, this is the VT reentrant circuit here, and then this is kind of all depolarized passively from the VT reentrant circuit. So we have a VT reentrant circuit, and our VT is dictated by our exit site. So let's imagine that we have VT morphology that's upright in lead 2, and the VT cycle length is 320 milliseconds, and that's dictated by the exit site. So imagine that we ablate this area, so this VT reentrant circuit can no longer occur. Let's imagine that we do that. So we find the exit site and we ablate it. What would happen? Well, now your reentrant circuit can't go like this, but it can change to this. And this is what happens sometimes when you ablate VT, is that you don't terminate VT, but you change its morphology and its cycle length. This is a longer circuit than this. So the VT cycle length will probably slow, and because the exit site is different, the VT morphology will change. So ablation of one exit can result in VT exiting a different exit site inside the scar, and that will change the VT morphology and cycle length. Now, because QRS complexes start around kind of the exit site, if you place a catheter at the exit site, you will measure electrical activity that occurs at or around the QRS onset, or just before the QRS onset. Because remember, you need to depolarize a critical amount of muscle mass before you get QRS onset on the ECG, right? You have to depolarize like at least this amount of tissue. So if you place your catheter here, then you might detect electrical activity just before the QRS onset, right? And we call that a pre-systolic EGM. Systole kind of refers to your QRS complex, and diastole kind of refers to the period between your QRS complexes. Now, depending on the health of the exit site, the health of the myocytes, if your myocytes are relatively healthy at the exit site, then your EGM may have a normal voltage and normal duration. But if the exit site has diseased myocytes, then your morphology of your electrograms may be complex, and they may be fractionated and low in amplitude or voltage. This is another example, and perhaps an example that's, I guess, I see probably more often. So here we have some VT. We have some VT occurring here. And here we have a VT reentrant circuit. Follow the colors of the rainbow again. This time you have to include white, because this particular 3D mapping company uses white. So you have white, red, orange, yellow, green, light blue, dark blue, purple. So we have depolarization rotating like this, and these black lines represent some kind of barrier. You know, maybe there's scar tissue there that's electrically inert, or maybe there's some kind of functional barrier for conduction. And if you look at the EGMs that are in this location at the tip of the arrow here, you know, so I'm going to draw a red circle. If you look at the EGMs in this location where depolarization exits these functional barriers and starts depolarizing the rest of the myocardium from this point, and you look at the EGM that you get an EGM that's not that prolonged and fractionated. So conduction velocity is not necessarily that slow here, but the EGM amplitude does look low. I don't know what amplitude it is because we don't have a voltage scale, unfortunately, but it looks kind of low. So probably not much voltage is being generated, but it's not super slow conduction velocity. And if you look at the timing of the EGM, it is about on time or just before QRS onset, which is in keeping with what we drew here. So this is an exit site EGM example.